Good afternoon, everyone. I'm Jeremy Picot-Clemente, Technology Manager at EPIC. I'm really pleased to welcome you for this EPIC member new product release today. A few words about EPIC. EPIC is the largest photonics industry consortium in the world with more than 800 members. So we act as a catalyst of the European photonics industry, and we offer to our members a wide range of services from technology support to access to different markets where photonics is involved. Including market reports, networking, mentorship, etc. Here is a quick overview on the next event EPIC will organize, so online and on site. So in November, a lot of events. If we talk about on-site meetings, so next week we'll have the technology meeting on microelectronics and photonics in Munich, Germany. We organize also a Tech Watch during Compamed. We have this technology meeting on cancer pathology and surgery in Belgium, end of November. We organize also a Tech Watch and a VIP breakfast at W3 Fair in Germany, in Jena. And at the end of November, beginning of December, we have also this members delegation to Malaysia and Singapore. And about online meeting, we organize so 2 OTM before the end of the year, one on new mid-IR developments for novel industrial manufacturing, the 20th of November, and another on food and beverages, the 11th of December. And then we have 2 work groups, one on sustainable photonics, the 8th of December, and the other one on HR, the 15th of December 2023. And then beginning of next year, we have another new product release meeting, the 9th of January. And before to start, we can have a look on the agenda of today's meeting. We will start with a presentation by Arántzazu Nuñez from AIMEN. Then we'll continue with Johannes Blöchl from UFI, Ultrafast Innovation. We have also a presentation from Altechna by Mantas Kulnickas. And after Altechna, we have VIGO Photonics with Paweł. And then we'll end this meeting with Optofidelity and a presentation by Murat, Deveci. So now we have 1 hour, and we start right now with the first presentation by Arántzazu Nuñez from AIMEN. So please, stop sharing, and Arántzazu, you can start your presentation. The floor is yours.
I hope now you can see my screen.
Yes.
Okay, so good afternoon. My name is Arántzazu Nuñez Cascajero, and I'm a researcher at the AIMEN Technology Center. Today, we want to present you our high-stability metal-coated optical fiber optics for distributed monitoring of high-temperature infrastructure. AIMEN is a private non-profit technology center that is located in Galicia at the northwest of Spain. We are specialized in materials and advanced manufacturing processes, working in technological services, offering solutions to clients, and also in research and development projects for different sectors such as metal, mechanics, automotive, aerospace, energy, shipbuilding, and also for biofood and textile. Our organization is member of different European and national associations, and in the last 10 years, we have participated in more than 690 research and development projects. In particular, the solution that is presented today has been developed by the Fiber Optic Sensor Group of the Smart System and Smart Manufacturing Research and Development Unit. But why does this technology arise? Because there are many applications where it is necessary to measure strain and temperature simultaneously. For it, fiber optic sensors are a well-known technology and also an established technology. Although the fiber optic is made with silica that withstand temperatures up to 1,200 degrees, the commercially available fiber optic sensors can be used for long-term monitoring and temperatures higher than 450 degrees due to the coatings that are used. Also, in harsh environments, their durability decreases drastically. So, a solution should be found for industrial processes that works in those high temperatures, and also for those sensors that doesn't need to withstand those temperatures, but that for the embedding process they need to withstand very high temperatures due to the melting of the materials. So this technology can be used in power generation, aircrafts, nuclear, and also in furnace and pipes of the metal casting applications. Frontier technology comprises a unique automated and continuous coating system for FPGAs and distributed fiber optic sensors. It is a unique technology in the market that is patent pending. The equipment allows the continuous coating of optical fiber with a wide range of coating thicknesses. It has different control and monitoring parameters such as temperature, coating speed, coating quality, tensile, and also it's very versatile because it can be used with other metals when optimized. And as I have commented before, it is usable for FPGAs and for optical fibers. Regarding the optical fiber that we can achieve and its properties, we can achieve homogeneous custom coatings as the one shown here. And the fiber that we achieve is very manipulable. They do not easily break or deteriorate. Also, you can see here other properties. The most interesting ones are the ones the ones that comprise the thermal performance, having a long-term temperature point of 700 degrees, and for short-term for 1000 degrees. These optical fibers can be embedded by welding, laser, ultrasound, and other techniques. Also, it is important to remark that it is a cost-effective product, it being cheaper than other alternatives, such as gold or sapphire. The nickel-coated sensors have been thermally tested, and both fibers, distributed fibers and FPGAs, show a repeatable and reproducible response in every test that we have done. Regarding the mechanical properties of the embedded sensors, we also have a very reproducible and repeatable response, it being quite comparable with those of the strain gauge. Finally, AIMEN has had the opportunity of test these nickel coating sensors in different applications. As fabricated, they have been tested in power generation, mainly for measuring temperature and strain in an energy storage concrete tank of a concentrated solar power plant. Also, they have been installed in a superheated biomass boiler and in a superheated combined cycle boiler for monitoring its temperature during 1 year operation. Regarding the embedded process, we have tested them in a multi-material offshore wind tower, where we embed the metallic optical fiber sensors to monitor the corrosion of the material, and also in the naval sector, where we embed the sensors to monitor the anti-friction material of a bearing. But as aforementioned, this technology can be also used for aerospace, railway, nuclear, and even for metallurgy. Regarding the commercialization of frontier technology, although the patent is pending, it will cover the fiber coating process and the implementing equipment, with particular focus on the monitoring and quality process of homogeneous custom coating. AIMEN is actually looking for licensing the technology, but small orders can be contracted for tests and pilots. We think that this technology may be interesting for special fiber optic manufacturers and also for optical fiber sensor manufacturers, which are interested in harsh environment. So, if someone that is interested on it, please do not hesitate to contact with us. Thank you for your attention.
Thank you very much, Arántzazu, for this interesting presentation. So do we have any question from the participants? So you can raise your hand through Zoom. So we work a lot at EPIC. We have a lot of at least several companies working in the field of optical fiber sensing, Arántzazu. So we will be pleased to put you in contact or to introduce you to these companies because I'm pretty sure that they will be interested by the technology you are providing.
Okay, thanks.
Okay, so if we don't have any questions, so we can move with our next speakers. So UFI Ultrafast Innovation. So Johannes, you can share your screen and start your presentation, please.
Okay, I hope you can see my slides. My name is Johannes Blöchl, and I'm working as a development engineer for optical systems at UFI. And today I'm going to present to you our Moderator, which is the single-shot CEP meter that we have introduced just a few months ago. And it allows you to measure the carrier envelope phase of few cycle laser pulses. But before I can jump into the details of the product, I would like to introduce our company a bit more. Our company has been founded as a spin-off from the Max Planck Institute of Quantum Optics and the Ludwig Maximilians University in Munich in 2009. And initially we started with the production of customized mirrors, where we actually cover the range from the IR to the XUV region, and we offer optics with different bandwidths to whatever the customer would like to have. We can make different spectral phases and also chirped mirrors. And after, basically this is what our company started with, but after some time we also established a second branch that is offering devices especially targeted to the ultrafast scientific community. Just as you see in the picture, for instance, an XUV spectrometer or other devices, which I will show to you in a second. And additionally to these devices, we also offer full assemblies, meaning that we sell complete experimental setups to scientists, also in this ultrafast scientific field. Just to give you a quick overview of the products we offer, we have our characterization product line with a third-order autocorrelator, white light interferometer, and cavity ring-down loss meter and reflectometer. Especially the Tundra is widely used in laser facilities to measure the pulse contrast. Besides these products, we also offer a bunch of other products which are important to scientists in attosecond physics or in ultrafast physics. Just to name a few, for instance, the K2 delay unit, which can be used as the generator of some pump probe measurements, or the light field synthesizer Capella, which is a rather tiny device, but it's doing some very interesting pulse shaping by splitting ultrafast laser pulses into different channels, compressing each channel, and then recombining those channels again. But today I'm going to talk to you about the Moderator, which is a CEP meter. And when I talk about CEP or carrier envelope phase, you might not be all familiar with this because this is a quantity which is especially important to scientists that work with these few cycle laser pulses. And whenever you ask such a scientist what carrier envelope phase is, he or she will draw a sketch that looks like what you see on the right-hand side. Namely, when you have a very short laser pulse, where the term short means that the envelope of the pulse is, let's say, just a few cycles, optical cycles long, then the carrier envelope phase, which is the offset between the field oscillation and the envelope of the pulse, becomes important. Because whenever you are dealing with some kind of light matter interaction, the electric charges that you manipulate always couple with the electric field of light. And this single quantity describes the shape of the electric field of light. And therefore, in this few cycle regime, you can describe the whole experiment as a function of this carrier envelope phase. And this is why this quantity is very important to scientists in this field. And our CEP meter can now measure this quantity, but not in a way that it needs a long acquisition time, but rather in a single shot way, which means that you send one isolated pulse to the device and it tells you the CEP. You can also do this with a pulse train, meaning that you send one pulse after another, which is usually coming from a laser system, and our device can then measure this quantity for each pulse in series. And this is very important because there are laser sources that produce short laser pulses, but that do not have a stable carrier envelope phase, which means that it changes from pulse to pulse. And if you do an experiment that depends on the carrier envelope phase, it is necessary to characterize or to measure this carrier envelope phase in a single shot way. But also for diagnostics of laser systems, it's important that you can actually verify that the carrier envelope phase of a system that is supposed to be carrier envelope phase stable is stable on a single shot basis. And our product is especially designed to fit to this titanium sapphire based laser systems, which usually have a wavelength or operate in a wavelength range from 500 to 1000 nanometers. And this is where our device works best. Our device offers a long-term stability, which is very important because it can measure the carrier envelope phase of each single laser pulse over a very extended period of time of several hours or up to several days. And here you see an exemplary data set. So each small blue dot here corresponds to a single laser shot. And when using this device, it's actually, in addition to a reference, you can actually verify that the measurement data of this device corresponds to the carrier envelope phase. And it's coming with the advantage that our device is sort of a one-to-one replacement to other commercially available devices, but with a much simpler approach, because previously the use of ultra-high vacuum was necessary and some MCPs. But our device is now measuring a similar or the same quantity with a much simpler approach, which makes it much more reliable in comparison to what has been on the market before. And with this, I would like to conclude and thank you for your attention. If you have any questions, please feel free to ask them right now or contact us under info@ultrafastinnovations.com.
Thank you, Johannes. Thank you very much for your presentation. Any question for Johannes, please? You can raise your hand through Zoom. What kind of market do you target with this product, Johannes?
The product is especially targeting the scientific community, but not only the scientific community, because nowadays the laser systems that scientists have been working for 10 or 15 years become commercially available. And therefore, potential customers are also laser companies which would like to characterize the laser systems. So in this case, this device would act as some characterization device, whereas for scientists, the device would be more like a device which is used or meant to be used in connection to another experiment to do some coincidence measurements, for instance.
Yeah, very interesting. Any question? Okay, thank you very much again, Johannes, and you can contact Ultrafast Innovation afterward, of course, or you can contact us if you want to be put in contact with Johannes or other speakers. So thank you again, Johannes. And now let's move on with our next speakers, Mantas Kulnickas from Altechna. So Mantas, you can start your presentation now.
Thank you, Jeremy. Let me share my screen. Yeah, just a moment. Okay. You can see it, right?
Yes.
Yeah, so as Jeremy presented, I'm a key account manager, Mantas Kulnickas from company Altechna. And during this short presentation, I will tell you about main principles of how our engineers at Altechna are manufacturing increased laser damage threshold transmissive optics by the help of ion pre-cleaning technology. So this will be just a help for transmissive optics, not reflective ones. But first, very shortly about what Altechna is offering for the market in general. We are a manufacturer of custom laser optics and custom optomechanical assemblies. So various dielectric coated optics on various shaped substrates is half of our business. So that's majority. Laser, nonlinear, and other crystals is around 10%. We also offer various polarization optics like wave plates, thin film polarizers, all polarizing cubes, as well as non-polarizing cubes. And increasing part of our business is customized optomechanical assemblies. So these are typically like build-to-print projects, or other people call them contract manufacturing. So our in-house optical and mechanical engineers help each of our customers to build the products they need, but we can also manufacture already designed products. These can be various optical components bonded together with other optical components and then mounted into various mechanical houses. High cleanliness requirements are not the issue, as we have brand new clean room area equipped with required metrology devices for full quality control. Assemblies can be measured and packed in a clean room without exposing them to unclean environment. Now let's proceed to the coating technologies themselves and my today's topic. So there are main three physical vapor deposition methods used commercially in the market. These are ion-assisted electron beam deposition, ion beam sputtering, and magnetron sputtering. And we have all of these main technologies in-house at Altechna. So it makes us really flexible when we need to offer the most suitable coating solution for the customer. Once we analyze any optical component, we always divided it into at least three main structure units, because most of the time they have different characteristics. So coating, subsurface of substrate, and bulk of the substrate. Of course, subsurface is not green, it's just for this visualization. How subsurface is formed. Once the bulk of the glass or crystalline material is cut and grinded, it finally has to be polished. Most common polishing technique is pitch polishing. It's also the most cost-effective one. And when that together with slurry is pushed towards the substrate by rotational movements. So yeah, simple polishing technique. So this force towards the bulk creates small cracks, which are filled with polishing slurry. Even after repeated cleaning of the substrate, these contaminants remain in the cracks. All these cracks and residual material form so-called Bailey layer, which acts as an absorption and scattering source. And that leads to limited damage threshold. Depending on the polishing quality, thickness of this layer can be like up to 10 microns. So it's really relative, depending on the polishing quality. To overcome this issue, our engineers have developed an pre-cleaning technique. I will not go into very details due to time limitations, but simply saying, first, substrates are loaded into a coating chamber. Then a strong ion beam is shot towards the surface of substrate, and a big portion of surface contamination, which I described in my previous slide, is removed. Afterwards, coating is deposited without opening the chamber, so forming all of the optical properties and also sealing the surface. Even though it sounds like an easy job, however, in real life, there are many factors and parameters influencing the outcome of this process. So it's really not that straightforward. After many trials and failures, we were able to achieve great results for transmissive optics. I will present just two examples. The first one is window coated with anti-reflective coating. Without ion pre-cleaning, typical LIDT values are somewhere around 25 joules per centimeter square. Meanwhile, with pre-cleaning technology, we repeatedly managed to achieve more than 67 joules per centimeter square. Damage threshold tests were done at 1064 nanometers, so increase was more than 2 times. Absorption was not influenced for this window and remained below 1 ppm, so same as without pre-cleaning technology. So these strong ion sources do not induce any additional absorption. The second example is a multi-wavelength AR-coated optical component. Without pre-cleaning, typically achieved value was 8.5 joules per centimeter square. When we scale the result to 10 nanoseconds pulse duration, because tests were executed at 5.5 nanoseconds, so we can rescale it to 10 nanoseconds, what is typically used in the market. And once we did pre-cleaning, we managed to achieve more than 21 joules per centimeter square, also scaled to 10 nanoseconds. So these measurements in this case were done at 532 nanometers. So these are just two very short examples of what we're able to achieve. So yeah, thank you for listening, and let's keep in touch.
Thank you very much, Mantas. Any question? I'm pretty sure that your technology will interest laser making companies. So any question for Mantas, you can raise your hand. I was wondering, Mantas, how many optical elements are you able to pre-clean at the same time?
So we can retreat as many as the chamber size. So it really depends on the component size itself. If it's 1 inch, around 400 pieces per single run.
Interesting. Yes, Dominique Bonisso from Photonics Biz.
Thank you very much. Mantas, I would like to know what is your opinion about metasurface, optical metasurface, with who could be very interesting in high LITD results. Are you thinking about that?
With metals, it's a little bit more tricky and not directly related to this topic, because these are reflective coatings and not also the electric ones. My guess would be that it would be mostly related to coated protective layer. So, yeah.
Okay.
But I guess metal coatings itself, they're not dedicated for the highest laser powers, just fundamentally, I guess.
Okay. I'll send you some information about that. Okay?
Okay, yeah.
Okay, thank you very much. Thank you.
Thank you, Dominic. Yes, Andreas comes from FISBA. Andreas?
Hello, thank you for the presentation. So can you disclose something about the type of ions, or is it just simple, or I know it's not that simple, argon ion that you shoot on out of the coating chamber, or is it something special regarding gas type you use?
Yeah, unfortunately, engineers were quite skeptical. I thought of getting this question actually, but sorry, I cannot disclose that one.
I understand.
Yeah, but everything is done within chamber, so. Yeah.
Thank you.
Thank you, Andreas. Any other question for Mantas? Yes, Anthony, Mani from Terastech. Please, Anthony.
Can you say if in the single wavelength AR film that you showed the damage threshold results, was that ion beam sputtered?
In this case, it was another technology. Yeah.
Sure. Thank you.
Not ion beam sputtering, yeah.
Thank you, Anthony, for your question. Okay, and thank you again, Mantas. Thank you for our presentation. And now welcome Paweł from VIGO Photonics. So Paweł, you can now start your presentation.
Okay. Okay. Do you see it right?
Yes, you can start.
Okay, so I will say a few words about the 3.5 detectors recently developed by VIGO. I'm head of product in VIGO, responsible for detectors, new products, and strategy. Feel free to contact me later after presentation to ask questions and just after. VIGO is a company located in Poland, so most of our customers are also located in Europe. But we have two large markets that are growing, North America and Asia. The company is on the market for 35 years, so it's quite a while. We offer sensors, infrared sensors for wavelength starting from 1 micrometer up to 20 micrometers, 16 micrometers, with different technologies, 3.5, MCT, InGaAs, which is a 3.5 based sensor, all available in VIGO. Our main advantage, I think, at least recently, when supply chains are kind of risky, is that we do everything in-house. We do epitaxy in Poland, we do processing in the same facility, we do packaging of detectors, and we can integrate them with electronics. Our electronics or electronics that are designed by the customer, it's all available, and this way we have a very stable supply chain setup. First product I wanted to talk about is the SMB product designed to be solderable, to use it together with other electronics. If someone is using already or building a device that should be small but see infrared, this is a very good starting point. It's a small package, 4 by 4 micrometers, and it is indium arsenide, so it can see up to 3.5, 3.4 micrometers. Detectivity is presented here on the right side, and it can work with standard soldering methods that are used for the electronics. Compared to other RF sensors, it can also work with wavelength that is smaller than 2 micrometers. Most of our sensors for longer wavelength cannot see any wavelength lower at a wavelength lower than 2 micrometers. The area, this kind of starting point for us is 1 micrometer, 1 square millimeter. But we can do them smaller, we can do them slightly bigger. It's up to the application. Products for a bit longer wavelength can be integrated with a preamplifier that is more or less the size of it. This is a TO TO39 package placed on the PCB that is actual the preamplifier. We have two versions of them recently implemented into a higher volume production. Version for 5 micrometers on the left side, the graph with detectivity, and for a bit longer wavelength, like 6 micrometers. Quite useful for spectroscopy with bandwidth up to 4 megahertz. That is fast enough to work with modulated lasers. And because it's a photodiode, it can also work nicely with low frequencies. Because 1/f noise is not generated by the current flow through the sensor. The sensor is not biased, and only source of the 1/f noise is related to the preamplifier. We've made it also a single supply, so it should be very comfortable to work with for the engineers for electronics that are designing the products. And because we tried to make it as comfortable as possible for R&D development, we also introduced a group of accessories that can be easily connected with the module. I will mention only a few. You will get that presentation later, but quite useful is the additional amplifier that can be just stuck on the preamplifier, and this way the gain of 10 times is generated. We have them in both two versions. One is AC coupled and one DC coupled. So any gain can be achieved using just a multiple amplifiers stack one on another. A few mechanical accessories and a digital accessory. Digital is analog to digital converter with interface. It can be a USB interface or SPI interface. It is also just stacked on top of the preamplifier, and we get a full signal in digital domain, keeping the frequency of 4 megahertz still available. This is how it looks when it's stacked all together. This is the heatsink that we can deliver preamp on the bottom, few additional amplifiers in series, and a simple connector for analog analysis using oscilloscope. And third, actually, product that I wanted to mention is a cascade detector. It's a type 2 superlattice based sensor optimized for spectroscopy at long wavelength. We have two versions, one up to 11 micrometers and second one up to 14 micrometers. The 11 micrometers, 10.6 actually, is also available as uncooled version. But what we see on the right, the detectivity is normalized. The normalized detectivity is shown for the 40E cooled sensors. They are at the beginning of the development, but we already offer sensors in smaller volume. And we see that the detectivity we reached is very promising, and further development will be continued here. Thank you. If you have any questions, I'm open and happy to answer.
Thank you, Paweł. Thank you for your presentation. Any question for Paweł? I was wondering, Paweł, you mentioned that you are making also the packaging of your detectors. Are you working already with space industries, and are you making packaging dedicated to space application?
Yes. VIGO was in contact with NASA, with ESA. We delivered some sensors. Some of them are still working on Mars. So we have some experience in that field. We can do that. We can also cooperate with companies. We have them also in Poland that can deliver electronics specialized to operate in space. So everything is within our reach.
Okay, interesting. Any question? Okay, so you can of course contact Paweł afterward, or you can contact us if you want to be put in contact with VIGO. So thank you very much again for your presentation. And then now the last presentation of the day from Murat Deveci and from Optofidelity. So Murat, you can start if you want.
Yeah, can you see the screen?
Yes, thank you.
Okay. Yeah, so thanks for organizing the event and for the introduction. My name is Murat Deveci. Today I will introduce one of our AR waveguide optical metrology systems, but let me first quickly introduce who we are. Okay, so we began in the early 2000s with test automation and display metrology. For the VR side, right after the introduction of the Oculus, we also introduced our first VR display metrology tester. Then with the debut of HoloLens, we also developed our first waveguide-based optical metrology station. Since then, we've delivered hundreds of different AR, VR, nowadays called mixed reality MR optical metrology stations. We are based in Finland, our headquarters is based in Finland, but we have a global presence. In US, we are located both in California and Washington states, and also in the APAC region, we have various different locations. In mainland China itself, we have more than 10 different offices and also production facilities in Taiwan, Korea, and all the neighboring countries. We are supporting our customers' production testing needs in the APAC region, in the Asia. We are supporting their R&D and product development related testing needs in both Europe and also in the USA, especially in the Bay Area. So we have a goal here, and we are almost reaching that goal. We are pretty much working with 95% of the all AR product developing companies right now, and we are supporting and supplying them with all their optical metrology and testing equipments, whatever they need when they are developing, designing, and also manufacturing in small volume nowadays, these AR smart glasses or mixed reality head-mounted displays. Let's jump on the next one. So as mentioned, we kind of want to be a one-stop shop for our customers' testing and metrology needs when they are developing and manufacturing this type of eyewears. So here are some relevant solutions from grading analysis to assembly of the waveguides, and today's focus, it will be the image quality. And today we will talk about that one. So that will be the focus of this presentation. So let's start by asking a simple question. And that the answer of that question will reveal the purpose of our product. So on the right side, you can see what is projected into an AR waveguide and the resulting virtual image that appears to the user. On the left side, you can see what is given from the input grading and what is taken out from the output grading. So the question is, does this waveguide produce a nice image? If so, how nice it is? Can you measure it? Can you quantify it? So this has been the main challenge faced by pretty much all customers, all companies who work on developing the AR smart glasses or any type of virtual reality head-mounted displays also. So before designing such optical metrology system for near-to-eye displays and their components, in this case, that is the waveguide or waveguide combiner, one needs to study the human eye very well, because simulating the human visual system will require the knowledge of the human eye and its performance data, such as the field of view, FOV, resolution, angular resolution, sharpness, contrast, then more mechanical data, such as the IPD, eye relief, eye pupil size, etc. So with that challenge on mind, our optical metrology team, they designed a lens that is replicating the large FOVs with the entrance pupil in front of the surface and with variable focus. Then we can also change the aperture to simulate different human pupil size variations, just like the human eye would do in any type of situation. Then we can attach a monochromatic camera or a colorimeter to this lens, and with the combination of these lens and the suitable camera, now this tool sees what the AR smart glasses user would see. It's a double imaging conoscopic lens having two aperture stops, one external for the camera and one internal for the projector, so that we can use it for both projecting something and then imaging something also out from the output grading. Since by adding a camera, we kind of turn this combination into a machine vision solution. Now we can have single shot imaging of the full field of AR waveguides, just like you would wear the glasses and you will see everything with your own eye, basically. With that kind of imaging data, now it is possible to really tell if that waveguide really produces a nice image or not. Let's jump on the next one. Then, of course, as a component, lens and the camera is not good enough. So because human eye moves around, so you have to also develop a very nice, very accurate robotic platform. So we designed such highly accurate robotic platform. So that also supports the extensive range of pentascopic tilts. In this case, it is up to 12 degrees already, and a certain degree of face wrap angles. So it's multi-axis, allow us to perform this type of world side and eye side measurements. And it's flexible, and we can also accommodate, for example, eyepieces, also called waveguides, dice waveguides, or the full size of wafers up to 300 millimeters. So with its various positioning cameras, it's also shown here in the diagram, and also the sensors, autocollimators, active alignment tools, and even a hexapod. These are all supporting its crazy good accuracy. So once this optical setup and the robotics are integrated, we kind of made this AR optical metrology system. It is going to be mainly used for R&D, but it's going to be so flexible, and it's going to be also providing a good enough speed so that it will be enough for even ramp up phase needs of the image quality testing. So with this new system, our customers now can measure various test metrics. It's click and run, and they can also implement their own algorithms for whatever the test case that they are working on. They can also measure that one because the hardware is there and the software is also allowing that. So these are the click and run test metrics. It's included its software suite. So checkerboard contrast, color uniformity, shift triangle, MTF, efficiency, I-box, FOV, geometric distortion, luminance. So these are the stuff that is, these are the most relevant ones when you are testing something in terms of its image quality performance. So some pictures here, these are the real pictures from a real commercial product, commercial head-mounted display. So this is what you get, and this is how you decide if your waveguide actually produces a nice image or not. So with this product, now it is possible to measure that. And it will cut down your design iteration tremendously, and it will also cut down your all the production costs, all the test costs, because now you have a kind of a tool that will immediately tell you that, okay, we've done all of this design. Now we have our gradings ready. We have our waveguide stack is ready. Let's just put it here. Let's just measure it. And it will tell us that, okay, this gives a good image and how good it is, because it will also provide you all the raw data, basically. And then this product will look like this. So it's already alive. So I also put here our YouTube link, so you can also watch it. I didn't want to put the video here because it's a very short presentation, but it is on YouTube. So yeah, this is how it looks like. There is at this moment nothing like this in the market. So we are quite proud of this product. Yeah, so if you have any questions related to this, please feel free to contact me. And this product is also available for demonstration purposes in the Bay Area, in Europe, and also in China. So anything is possible. If you have some samples that you are interested in its performance data, please get in touch with me. We can make some measurements for you. Thank you very much for listening.
Very good. Thank you very much, Murat, for this last presentation on this product. Really relevant for this industry. So any question for Murat? So this product, Murat, is dedicated to measure components, but are you able also to do this kind of measurement on the global system? You know, like the headset, directly on the headset or directly on the air?
Yeah, so for the fully assembled headsets, if you are referring to that, so same lens and same colorimeter and the different cameras can be used. But for this particular product, it's for component level testing. So before you actually assemble the whole thing, so first you have to decide that this waveguide is good or not, so that you move on to the next phases. Yeah.
So your targeting customers could be system integrators or waveguides manufacturer, for example.
So all the brand owners, when I say brand owners, the companies, they have their own head-mounted markets, or waveguide design houses, waveguide design companies who own the design IP for the waveguides, or integrators. They are actually manufacturing for the brand owners, and they need to have the tools to measure the waveguides during the assembly phases. Yeah.
Okay, great. Any question for Murat? So we will it's a good opportunity to announce that we'll organize a technical meeting next year in 2024, end of May, on AR/VR market and photonics for AR/VR. It will be hosted by Microsoft in Finland, and I think that Murat will be there as well. So yeah, any question? Okay, so feel free to contact us or to contact the speakers. You can also contact me, and I will be pleased to put you in to introduce you to the speakers. So I would like to thank all the speakers for making it possible. A really interesting presentation, and also all the participants. Thank you very much to all of you, and see you next time for another EPIC event. Thanks a lot. Bye bye.